In a classic blockchain system, every node maintains the entire blockchain, including both the blocks and their headers. But this is not scalable due to its expensive storage and communication costs. Thus, a scalable blockchain system should also admit a new type of nodes that only store the headers. Such nodes are called light nodes. A light node could be a client in a simplified payment verification system, or a node from a different shard in a sharding blockchain system. But since a light node does not download any blocks, how can it decide to accept a block header or not? The classic solution is simply wait. A light node waits until the block to be deeply buried in the blockchain before accepting its header. In our example here, a light node waits for 4 epochs before accepting a block header. In general, longer waiting yields higher confidence. However, this method has an obvious disadvantage, a very high confirmation latency that could be hours. A more promising approach is to build a blockchain system where light nodes can rely on honest full nodes in the system to alert them about invalid blocks. This way, a light node can set a short timer based on the network latency, and if it does not hear any alarm against a block before the deadline, it will accept the block header. However, this solution also has a hole. An adversary block miner can attack light nodes by publishing the header of an invalid block but hide the block body, so that honest full nodes cannot audit the block body and alert the light nodes. This attack is called data availability attack. Due to this attack, before accepting a block header, a light node must first check by itself that the entire block has been published and is available for auditing. But data availability check is very difficult. This is because an adversary miner only needs to hide a very small portion of a block to hide a fraud transaction. Such a small hiding can hardly be detected by a light node unless the light node downloads the entire block, which is not allowed. At Trifecta Technology, we solve this data availability attack by inventing a novel hash accumulator called coded Merkle Tree, which allows light nodes to check the availability of any block at a constant cost, and it requires minimum changes to the system. To construct a coded Merkle tree, once a block is mined, the miner is required to equally partition the block into a set of base layer data symbols. These data symbols are then linearly combined to generate some parity symbols for the base layer, which is a process known as erasure-coding. The miner then computes the hashes of these base layer symbols and then batches these hashes into the data symbols of the second layer, which are then coded using a shorter erasure code. The iterative erasure coding and hashing process continues until the root of the tree is obtained, which is then included in the block header and sent along with the block body. So, how could coded Merkle tree help with data availability check? Since every layer of the tree is protected by an erasure code, every layer can be recovered even if a fairly large portion of it is missing. Therefore, to prevent the recovery of a layer, the adversary miner must hide a substantial portion of this layer. In this case, when a light node randomly samples the base layer data and parity symbols and their Merkle proofs, it is very likely that you will sample a missing symbol or a missing hash. This likelihood increases exponentially with the number of samples, which means that the total sampling cost is almost constant for any confidence level. In addition, coded Merkle tree is also tamper-proof. This is because honest full nodes of the system can recover the entire tree layer by layer from the top. Once a layer is correctly recovered, the hashes it carries will be used to verify the recovery of the next layer, If a recovered symbol does not match with its hash, then the miner is caught cheating in the tree construction. In this case, a constant size proof can be published to alert the light nodes. In summary, coded Merkle Tree protects light nodes of blockchain systems from data availability attacks at a constant cost per block. To enable this protection, we only need to add the root of the tree to the block header or to a special smart contract. The tree itself does not need to be published. Moreover, while coded Merkle Tree is invented to scale blockchain systems, it can also be applied to any decentralized systems that may be vulnerable to data hiding.